Instruction-level parallelism. Instruction-level parallelism, ILP, is used to refer to the architecture in which multiple operations can be performed parallelly in a particular process, with its own set of resources, address space, registers, identifiers, state, program counters. It refers to the compiler design techniques and processors designed to execute operations like memory load and store, integer addition, float multiplication, in parallel to improve the performance of the processors. Examples of architectures that exploit ILP are VLIW's superscalar architecture. ILP processors have the same execution hardware as RISC processors. The machines without ILP have complex hardware which is hard to implement. A typical ILP allows multiple cycle operations to be pipelined. Example: suppose 4 operations can be carried out in single clock cycle. So there will be 4 functional units, each attached to one of the operations, branch unit, and common register file in the ILP execution hardware. The sub-operations that can be performed by the functional units are integer ALU, integer multiplication, floating point operations, load, store. Let the respective latencies be 1, 2, 3, 2, 1. Let the sequence of instructions be sequential record of execution versus instruction-level parallel record of execution. Fig. A shows sequential execution of operations. Fig. B shows use of ILP in improving performance of the processor. The notes or the no operations in the above diagram are used to show idle time of processor. Since latency of floating point operations is 3, hence multiplications take 3 cycles and processor has to remain idle for that time period. However, in Fig. The processor can utilize those NOPs to execute other operations while previous ones are still being executed. While in sequential execution, each cycle has only one operation being executed. In processor with ILP, cycle 1 has 4 operations, cycle 2 has 2 operations. In cycle 3 there is NOP as the next 2 operations are dependent on first 2 multiplication operations. The sequential processor takes 12 cycles to execute 8 operations, whereas processor with ILP takes only 4 cycles. Architecture. Instruction-level parallelism is achieved when multiple operations are performed in single cycle, that is done by either executing them simultaneously or by utilizing gaps between 2 successive operations that is created due to the latencies. Now, the decision of when to execute an operation depends largely on the compiler rather than hardware. However, extent of compiler's control depends on type of ILP architecture where information regarding parallelism given by compiler to hardware via program varies. The classification of ILP architectures can be done in the following ways. Sequential architecture. Here, program is not expected to explicitly convey any information regarding parallelism to hardware, like superscalar architecture. Dependence architectures. Here, program explicitly mentions information regarding dependencies between operations like dataflow architecture. Independence architecture. Here, program gives information regarding which operations are independent of each other so that they can be executed instead of the NOPs. In order to apply ILP, compiler and hardware must determine data dependencies, independent operations, and scheduling of these independent operations, assignment of functional unit, and register to store data. Advantages. Improved performance. ILP can significantly improve the performance of processors by allowing multiple instructions to be executed simultaneously or out of order. This can lead to faster program execution and better system throughput. Efficient resource utilization. ILP can help to efficiently utilize processor resources by allowing multiple instructions to be executed at the same time. This can help to reduce resource wastage and increase efficiency. Reduced instruction dependency. ILP can help to reduce the number of instruction dependencies, which can limit the amount of instruction-level parallelism that can be exploited. This can help to improve performance and reduce bottlenecks. Increased throughput. ILP can help to increase the overall throughput of processors by allowing multiple instructions to be executed simultaneously or out of order. This can help to improve the performance of multi-threaded applications and other parallel processing tasks. Disadvantages. Increased complexity. Implementing ILP can be complex and requires additional hardware resources, which can increase the complexity and cost of processors. Instruction overhead. ILP can introduce additional instruction overhead, which can slow down the execution of some instructions and reduce performance. Data dependency. Data dependency can limit the amount of instruction-level parallelism that can be exploited. This can lead to lower performance and reduced throughput. Reduced energy efficiency. ILP can reduce the energy efficiency of processors by requiring additional hardware resources and increasing instruction overhead. This can increase power consumption and result in higher energy costs.